Energy often travels in the form of electromagnetic radiation, which is a wave. And being a wave, it's going to operate the way normal waves do. It's going to have three characteristics. It's going to have a speed, a wavelength, and a frequency. The only difference between electromagnetic radiation waves and waves that I've dealt with in the past is that the waves of electromagnetic radiation all travel at the same speed, which is the speed of light, c. So I would set it up the way I would a normal wave, but instead of it being to an unknown velocity, it's actually a known velocity. The velocity is always the same. It is equal to the speed of light. And that's what this equation is saying. A wave is, as I said, three parts. It's a velocity, it's a wavelength, and it's a frequency. Now the frequency, the cycles per unit time, or the cycles per second, multiplied by the length of those cycles gives me a velocity. So I have a length multiplied by a frequency, some number of waves per second, and that will give me a velocity in meters per second. Now this n has no units, it's just whatever the frequency is. So since this is held constant, it also gives me another relationship that I normally don't have when I'm dealing with an arbitrary velocity. And that would be that the wavelength is inversely proportional to the frequency. Since both of these are going to multiply to be the same number every time, the same velocity, as one of these increases, the other one is going to decrease proportionally. So if I double my wavelength, then my frequency is going to decrease by half. If I multiply by my frequency by 4, then my wavelength is going to be divided by 4. And that's what this attempts to illustrate here. If this were to be a constant velocity for all of these waves, as the frequency begins to increase, the wavelength becomes smaller and smaller. And besides that, there really isn't a whole lot more to it. It's just a normal wave.